Hi everyone, welcome to today's topic Fibonacci numbers. Fibonacci numbers are not new to you and they have fascinated people for ages. Whatever we say here will never be enough. So let's start with a little history of how they came into being. In 1202, Fibonacci posed a problem in his Liber Abaci. The problem was like this: a pair of rabbits are placed at a place. How many pair of rabbits can be produced by the pair in a year if every month each pair bears a new pair, which from the second month becomes productive? Fibonacci wrote three books. Out of those three, Liber Abaci deals with arithmetic. Abaci here means calculation. His all three books were recognized by the European Federation. Let's try to understand the problem. If we denote by Fn the number of pairs after n months, then F1 will be 1 and F2 will be 1. After 2 months, this pair bears one pair of babies. If we write all the months, January, February, etc., and we start with January. In the month of January, we have just one pair of adults. Now, this pair of adults cannot produce babies because they are not 2 months old. So, number of the pair of babies is 0. In the month of February, still we have one pair of adults and there are no babies. So 0 pair of babies. In the month of March, now they are 2 months old. So we have one pair of adults and they give birth to one pair of babies. In the month of April, we still have only one pair of adults and the same pair of adults gives birth to another pair of babies. So if we add one to this previous one, we will get two. Now, in the month of May now, one of the pairs of babies from here becomes mature enough to give birth. So we have now two pair of adults and the number of pairs of babies is 3. This is how it goes. If you take the total in January, the total number of pairs of adults and babies is 1. We are adding 1 plus 0. In February, it is 1. In March, we have 1 plus 1, 2 pairs. In the month of April, we have 1 plus 2, 3 pairs. In the month of May, we have 2 plus 3, 5. So that is how it goes. Let's write the total number of pairs once again. So we are starting with 0. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. That is how it goes. Look at the numbers closely. You will see that when we start with this 1 and to that we add the previous number 0, we will get 1. So this gives us this 1 which is in the third place. Now to the next number 2, you add this previous number, that will give us 3. To this 3 you add the previous number 2, you will get 5. To this 5 now you add 3, that will give us 8. To 8 you will now add the 5 and that will give us 13. So this is how by adding the previous number we get the next number. So these numbers are known as Fibonacci numbers and you get a sequence. We also call it the Fibonacci series. These numbers have a fascinating property. Any Fibonacci number except the first two is the sum of two immediately preceding Fibonacci numbers. So what is the process? At any month after first two, total number of pairs is number of pairs in the previous month plus the number of newborn pairs. This gives rise to a recursive formula. Fn is equal to f of n minus 1 plus f of n minus 2 where n is greater than equal to 3. Fn here gives us the Fibonacci numbers. This sequence was named by Edward Lucas in the 19th century after Fibonacci. His name actually was Filius Bonacci, which means son of Bonacci. He was also called Leonardo of Pisa as he was born there. In 1843, Jacques-Philippe Binet gave a formula for Fn. His formula was Fn is equal to 1 upon root 5 alpha to the power n minus beta to the power n, where alpha and beta were the real roots of the quadratic x square minus x minus 1 is equal to 0 and alpha as 1 plus root 5 by 2 and beta as 1 minus root 5 by 2. Note, Fibonacci numbers grow faster than a geometric progression with common ratio alpha is equal to 1 plus root 5 by 2. Let's look at some results. The first result is by Gabriel Lame, it gives us the lower bound on the growth of Fibonacci numbers. Fn is always greater than alpha to the power n minus 2 for all values of n greater than equal to 3, where alpha is nothing but 1 plus root 5 by 2. The second result is on the upper bound of Fn. For every n greater than equal to 1, Fn is always less than alpha to the power n. Let's look at the third point. Each non-negative integer n can be uniquely written as a sum of non-consecutive, positive, distinct Fibonacci numbers. That is, n is nothing but summation k value 0 to infinity alpha k f of k. Let's look at an example. If you take 8, you can write 8 as 5 plus 3. You know that 8 is nothing but f of 6. What is 5? F of 5. And what is 3? F of 4. So every positive integer n can be written like this. This sum is known as Zeckendorf representation. The next point. No two successive Fibonacci numbers fn and f of n plus 1 have a common divisor d greater than 1. Next, the sum of first n Fibonacci numbers is nothing but f of n plus 2 minus 1. Then, the Cassinis formula. F of n minus 1 into f of n plus 1 minus fn square is always minus 1 to the power n, where n is greater than equal to 1. Let's look at the seventh point. The GCD of Fibonacci numbers is a Fibonacci number. 8. No Fibonacci number is a perfect number. 9. In a Fibonacci sequence, fm divides fn if and only if m divides n for n greater than equal to m greater than equal to 3. 10th point. The product of any four consecutive Fibonacci numbers is equal to area of a Pythagorean triangle. And 11th, limit of f of n plus 1 upon fn as n tends to infinity is always alpha, which is nothing but 1 plus root 5 by 2, which is the golden ratio. So this is how golden ratio and the Fibonacci numbers are related. Now look at this result. If p is a prime such that p is greater than 5, then either p divides f of p minus 1 or p will divide f of p plus 1, but not both. Next, if p is a prime which is of the form 4k plus 3, or you can say that p is congruent to 3 mod 4, then p cannot divide a Fibonacci number with an odd index. That is, p does not divide f of 2n minus 1 for all n greater than equal to 1. This is also used to prove that there are infinitely many primes of the form 4k plus 1. Now look at this beautiful result. 5 fn square plus 4 minus 1 to the power n is always a perfect square. Next, fn divides f of mn for all m and n greater than equal to 1 if GCD of m and n is 1. Next, see, if fm divides fn, then the remainder r is always a Fibonacci number, or f of m minus r is a Fibonacci number. Now let's see the growth of Fibonacci numbers of the form f5n plus 2. They will always be greater than 10 to the power n for all n greater than equal to 1. Take n is equal to 1, you get f7c. f of 7 is greater than 10 to the power 1. Take n is equal to 2, you get f of 12, which is greater than 10 to the power 2. You can check the rest of them. Next, few Fibonacci numbers are squares like f1 which is 1, f2 which is 1, and f12 which is 144. Now, this Fibonacci number has a beautiful property. You can always write it as a sum of 2 factorials. 5 factorial plus 4 factorial. Some of them are cubes like f1, f2 and f6. Some of them, in fact, only 5 are triangular numbers like f1, f2, f3, f8 and f10. If p is a prime of the form 5k plus minus 2, then p divides f of p plus 1. And if it is of the form 5k plus minus 1, then p divides f of p minus 1. Next result is also very interesting. F of 2n plus 2, f of 2n plus 4. If you take the product of these, it is product of 3 consecutive Fibonacci numbers with even indices, and this will always give us a product of 3 consecutive integers. Now look at this. If f of n plus 3 is congruent to fn mod of 2, then Fibonacci numbers of the form f of 3n. If I take n to be 1, 2, 3 and all, you will get f3, f6, f9, etc. They are all even integers, and f of n plus 3 will always be congruent to 3 f of n plus 1 minus f of n minus 1 for all values of n greater than equal equal to 2. See, you have another result where if 2 divides fn, then 4 will always divide f of n plus 1 whole square minus f of n minus 1 whole square. And if 3 divides fn, then 9 will divide f of n plus 1 cube minus f of n minus 1 cube. Next result is also quite interesting. If p is not equal to 5, that is for all other prime except p is equal to 5, f p minus 1 and f of p plus 1 is divisible by p. Now look at this result. If f of n plus 5 is congruent to 3 fn mod of 5, then all the Fibonacci numbers of the form f5n, that is f5, f10, f15 are all divisible by 5. Now based on our point number 9, you can see 2 divides fn if and only if 3 divides n, 5 divides fn if and only if 5 divides n, and 8 divides fn if and only if 6 divides n. So there are so many of them, but we will stop here. Let's come to some identities. The first one, fn is equal to f of k plus 1, f of n minus k plus fk f of n minus k minus 1, where n is greater than k plus 1 greater than 1. Let's take some particular values for n and k and just check this identity. If we take n is equal to 5 and k is equal to 2, then when we put these values in the formula, we will get f of 5 is equal to f of 3, 2 plus 1, f of 5 minus 2 plus f of 2, f of 5 minus 2 minus 1. Now which means f of 5 is equal to f of 3 into f of 3 plus f of 2 into f of 1. Substitute the values. You know that f of 5 is 5, f of 3 is 2, so we get 2 square plus f of 2 and f of 1 both are 1, so we get this as 5. Left hand side is equal to the right hand side. Look at the second identity. F of m plus n is equal to f of m minus 1 into fn plus fm f of n plus 1. In the third identity, you can see we have taken all the Fibonacci numbers with odd suffixes and we've added them. This sum comes out to be nothing but f of 2n. In the fourth one, we have taken all the Fibonacci numbers with even suffixes and we have added them. This sum is nothing but f of 2n plus 1 minus 1, or summation n value 1 to infinity f of 2k is equal to summation k0 to infinity n minus k f of 2k plus 1. Let's come to the fifth identity. Here we have added all the Fibonacci numbers but with alternate plus and minus sign, and this sum is nothing but 1 plus minus 1 to the power n plus 1 f of n minus 1. In the sixth identity, we have taken f1 plus 2 times f2 plus 3 times f3 dash 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 plus n f of n, and this comes out to be nothing but n plus 1 f of n plus 2 minus f of n plus 4 plus 2. In the seventh identity, we have taken all the Fibonacci numbers of the type n f of 2n. So now f2 plus 2f4 plus 3f6 dash 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 plus n f of 2n is equal to n f of 2n plus 1 minus f of 2n. In the eighth identity, we have taken square of all the Fibonacci numbers and added them, and this comes out to be fn f of n plus 1. In the ninth one, we have taken the sum of the products f1 f2, f2 f3, f3 f4 dash 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 f of 2n minus 1 into f of 2n, and this comes out to be f of 2n square. In the 10th identity, we have fn square plus f of n minus 1 whole square is equal to f of 2n plus 1. Look at the 11th identity. Here we have f of n plus 1 into fn minus f of n minus 1, f of n minus 2, and this gives us f of 2n minus 1 for all values of n greater than 2. In the 12th one, we have f of n plus 1 whole square is equal to 4fn into f of n minus 1 plus f of n minus 2 whole square, and this is for all values of n greater than 1. Look at the 13th identity. Fn square minus f of n plus 1 into f of n minus 1 is equal to minus 1 to the power n plus 1 f1 whole square. Now as you know that f1 is nothing but 1. This means that the difference of the two terms on the left hand side will always give us either plus 1 or a minus 1. In the 14th identity, we have taken the sum of the reciprocals. So summation n value 2 to infinity 1 upon f of n minus 1 into f of n plus 1 will always be equal to 1, and summation n 1 to infinity fn upon f of n plus 1 f of n plus 2 will always be again 1. The 15th one gives us summation k is equal to 0 to infinity. The binomial coefficients nk, f of k will always be equal to f of 2n, and summation k is equal to 0 to infinity. Binomial coefficient nk 2 to the power k fk is equal to f of 3n. These identities were given by Cesaro. So these were some of the identities. As I said in the beginning, people have always been fascinated by these numbers because they are so unique. And this is evident by so many results and identities which they have proved. So much so that there is an association of Fibonacci enthusiasts which was founded by Brother Alfred Bruce and Werner E. Hogarth Jr. in 1963. Those who are interested can check the website. You will get plenty of material to read. Thank you for watching. Story does not end here. There is so much to be said about the Fibonacci numbers that in our next video we will talk about the applications of Fibonacci numbers and some of the puzzles. For detailed notes and practice problems and my class lectures, you can visit my website www.profpreetibajpai.com.